Hi guys, welcome back to my YouTube channel. Myself Sahil, studying in SVCE College of Engineering, Bangalore from Department of Computer Science and Engineering, and I am currently pursuing in third semester Chanakya section. And today we are discussing about operating system, course code BCS 303, and here we are discussing about IEEE research papers. Topic: porting a safety critical industrial application on a mixed criticality enabled real-time operating system. Moving on to introduction. Since the seminal paper by Wistel in 2007, a large number of scientific papers related to mixed criticality scheduling techniques have been published. Even the Apollo guidance computer developed in 1966 and embedded in the Saturn V rocket had a primitive form of criticality management which took effect during the moon landing stage. The Imicrosser project targeted the creation of a version of the Hipparcos real-time operating system under two main requirements. First, porting the OS to a PowerPC multi-core platform brought by Thales Research and Technology. Second, to operate with a multi-mode isolated mixed criticality scheduling policy in order to provide predictable hard real-time guarantees. In this paper, we present the system architecture providing isolation between different criticality applications and the experiments validating our solution. Next we can see use cases. This research is largely based on an industrial use case provided by Thales Research and Technology. The use case was an application written in C++ and structured into multiple recurrent communicating tasks. The use case itself was largely comprised of tasks that would be certified at one assurance level. However, the aim of this research was in part to show that given an existing industrial application, applying mixed criticality techniques could lead to additional features at least little cost. The task set consisted in essential two types of tasks. First, many sensors like applications retrieving exterior information about the system. It is supposed to be embedded in. Second, a few heavier tasks doing database operations and distance calculations. Next we can see mixed criticality model. This section goes into the details of how the multi WCET and related techniques for mixed criticality scheduling were designed. Task types, mode switching, mixed criticality scheduling algorithm. First we can see task types. The system supports three types of tasks: highly critical task, real-time task, and best effort task. Best effort tasks are free to released at any rate and to consume an arbitrary amount of computation time. However, they will be considered with the lowest priorities by the scheduler and may therefore not get the resources needed to perform their purpose within strict time bounds. Yellow tasks have design time, defined periods, deadlines, and worst case execution times. Next, we can see mode switching. Two modes of operations are defined. Under normal circumference, the system uses all resources as efficiently as possible. Best efforts tasks are allowed to run with no constraints and compressible real-time tasks are released at nominal rate. Whenever a highly critical task overruns its LOWCAT, the system enters a critical mode of execution. In critical mode, best effort tasks are suspended and comprise real-time tasks have longer periods. Some composable tasks may have application-defined maximum delays between job releases, such as lower bound on the updates frequency of a sensor. Next, we can see mixed criticality scheduling algorithm. In the literature, mixed criticality task system are often considered in tandem with variations on either fixed priority scheduling or deadline driven scheduling. Indeed, the mode switch mechanism described above alone does not guarantee anything, as it might already be too late to execute a highly critical task to computation before its deadline. When a mode switch occurs, however, we did not implement these techniques in the context of this work. Only the mode switching system required by switch such a scheduling algorithm such as implemented, and it is applied in our experiments with a simple parameterized static priority scheduler. Next, we can see experiments. What are the experiments? We can see hardware platform experimental design, the task set effect of the LOWCET per core utilization. Conclusion. In this research, we ported an existing industrial use case application from Thales Research and Technology to the Hyperus RTOS. We developed the mixed criticality tensions extensions to the existing Hyperus kernel, adding support for the elastic mixed criticality model. We used the mixed criticality system of Hyperus and actual executions of Thales use case to show how much CPU time is available on the platform for low criticality tasks. Our data illustrates that the WCET bound evaluation techniques applied on highly critical tasks can be mitigated efficiently. A significant load of low criticality tasks can be added at little cost and number of OS level risk to the original applications. The OS does not guarantee that there is no interference between low criticality and high criticality tasks, but it does guarantee that low criticality tasks are suspended when high criticality tasks execute for longer than their typical duration as chosen by the user. Thank you.